in 94. Been working for the city ever since. As manager, as you can see, the asset management planning, but he's the manager of that asset management planning. Anything goes wrong with the city asset, it's his problem.
Except for transit.
Which is why he's like me.
That's right. Exactly.
So he's going to talk to us about the issues related to trying to make the city less reliable on one water main and create some redundancy in the system. So Steve, go ahead.
Thanks, Nigel. It is true. Thanks everybody. Exactly as Nigel says, my name is Steve Wyton. I've been the manager of asset management planning for, goodness gracious, about 23 years, and with the City of Calgary in various capacities for about 31 years. So I'm going to be excited when I get to sit on that side of the table. I'm looking at actually considering retirement in the next year, a couple of years. So I'm quite excited. It's been a true pleasure to serve Calgarians. I've been a Calgarian, was born and raised as a Haligonian. But moved to Calgary in about 1980. So yeah, yay, Halifax. But that's different challenges on the infrastructure altogether. So yes, I've been the manager here for asset management planning now in this new role where we actually have centralized all of our asset management offices. So about 3 years ago, we had disparate asset management offices, one for transit, one's for roads and water and IT, et cetera, et cetera. About 2.5 years ago, we reorganized and all of the asset management offices then fell under me. So Nigel's right, we run about $100 billion organization. That's billions. And so it spans everything from all of our facilities assets, if it's rec centers, community associations, the city offices, we have about 750 buildings. If it's road network, we have about 18,000 kilometers of roads, about 6,000 kilometers of sidewalk, about the same on underground. So if it's storm sanitary or water infrastructure, about 6,000 kilometers, 6,000, 3,000. And as well too for bridges, even the +15 network downtown that you might walk over periodically. So what my team does, we're split to allow all of our engineers to do condition assessments periodically at various frequencies, depending on the criticality of the asset. We assess those assets for performance based on risk. And then we make recommendations to City Council for the amount of money that we should be investing in any one of those asset portfolios. So it's a fascinating journey. My journey into understanding more about pipes really started with the water main break. I remember it was about 7:35 on a Thursday night. I was actually having a malted beverage, down in my basement, enjoying a Netflix show, and I got the phone call. You need to come down here. Something's going on. We lost pressure in one of Calgary's largest pipes. This pipe services 1.2 million people, not just within Calgary, but as well too is around the region. So Airdrie to Chestermere as well. So it's a massive pipe, 1,950 millimeters in size, and it doesn't have redundancy. So we'll talk a little about some of the challenges. We'll tell you a little about through the presentation here today about the pipe, why the pipe failed or why we think it failed. There's still forensic analysis going on now, what we're doing about that, and specifically talk about how we're trying to build redundancy both around the pipe and fix the pipe itself. All of this information, I will admit that we are still being scrutinized both by APEGA, we're under a practice review. As you would expect, we should be under practice review, as well as we're also under an independent review. So the information I'm sharing with you tonight, all is available in the public domain. And I'll do my best to answer if there's questions or talk a little of some of the stories. But I'm also mindful that there's some information that I'm just not able to share, and I hope you understand. Please, let's keep going here. So, okay, let's see. Is this gonna work? Oh boy, it's not working. So hang on. Let me see. Maybe I'm on the wrong. There we go. So a little about what I was just talking about as well too. All the information here is in the public domain. We're going to talk about the results of the Bearspaw South Feeder main pipe investigation, as well too as how the city plans to build system capacity. That's at a system level, as well too as asset redundancy around the Bearspaw Feeder main. And as well to talk about some of those infrastructure projects that are also going to provide growth for Calgary and the region, and what our next steps are for ensuring reliability of the feeder main. So let's talk, as I said, love to geek out a little with you all and talk about the pipe investigation itself. So as many of us are aware, on June the 5th, 2024, the Bearspaw South Feeder main suffered a catastrophic failure. The feeder main is most important within the City of Calgary's potable water transmission network. As I said, it consists of a 1950 millimeter PCC pipe, so it's a pre-stressed concrete cylindrical pipe, and as well to a 1500 millimeter pipe. Both of those were constructed in 1975, so almost as old as I am. Immediately following the rupture, the city requested that Associated Engineering provide us assistance and undertake an investigation as to the failed pipe and present the information gained during the exposure of additional pipes, also known as the 5 hotspots during the initial failure. The cause of the June 5th failure was breakage of a sufficient number of pre-stressed wires in a pipe segment, causing a loss of pressure resisting capability in the pipe. Based on the information available, we believe that the ruptured pipe experienced micro cracking or previous mortar damage, allowing for soil interaction with the pre-stressed wires. The micro cracks are, of course, if you're familiar with the construction of PCC pipe, micro cracks are small cracks within the outside mortar layer that are invisible to the naked eye, but still allow the external environment to become in contact with the wire wraps. The compromised mortar allowed for stress corrosion cracking and or hydrogen embrittlement of the pre-stressed wires, resulting in brittle wire failures and fractures. In fact, actually, we totaled that were approximately 200 wires that had failed within the pipe, and there were over 400 wires within an entire 16-foot section. So roughly half of the pipe, the wires had broken within the structure itself. So in other words, some of these pipes, the mortar is actually susceptible to either sulfide attack and or for chloride attack. So the chloride attack on that outside mortar. Therefore, what we're seeing is there's some way that the chlorides from the outside soils had penetrated most likely through those micro cracks that we weren't able to see. Some of the things that did not contribute to the failure, first off, is there's no information indicating that the manufacturing standards applicable in 1975 were not followed. I know that there were some of our counselors that were trying to attest that we had substandard materials of 1975. Some of them went so far as to say that the pipe that was built in Quebec, manufactured in Quebec, was susceptible to lower quality steel because of steel issues in Montreal and Quebec at the time, and that is definitely not the case. We had followed all of the necessary testing at the time and all of the construction standards of the time as well too.
Steve,
please.
That picture,
yes.
the cracks in the mortar layer, is that as you found it, or is that because you've excavated?
So actually that is found, that is on site. And actually that's a great question. I can't answer your question, Nigel. If it's because of it was unearthed and it spalled, or was it in the place? My guess is actually spalled post when we started unearthing. Exposing the pipe itself, and it just started falling off. The reason why I suspect that is we actually had that occur on another location, just at Crowchild Trail, a little further down, and I can give you a little more information about that. Of course. Live loading, and actually I will say as well too, if you'd like, we can just take questions as we walk through the presentation. If there's anything that I'm aware of, I'll just pause you and just say, hey, we'll catch this a little further on in the presentation. We also found that live loading subsequent to the construction in 1975 was not believed to be a contributing factor, and as well too, stray current induced corrosion does not to be present in the vicinity of the pipe break. Interestingly as well too, we did need to rule out the fact that pump operations from our plant was as part of the factor of the failure, and we identified through transient analysis that both the pumps at the Bearspaw water treatment plant as well too as the secondary pump stations did not create an under or overpressure situation that contributed to the failure. And that, as I said, a transient pressure event did not occur immediately before the rupture.
Doesn't share a right of way with the power line?
There were power lines adjacent to, and that's why we were wondering if there was stray current issues. But no, definitely, most definitely not.
Steve, was there any indication of stress corrosion cracking in the wires?
I'll get to that
Okay.
because that's actually, maybe I'll give you the short answer before I get to that in the presentation. Unfortunately, and this is part of forensic analysis, we found some parts of the pipe that had hydrogen embrittlement and or stress corrosion cracking, but there was no evidence of structural deficiency within the pipe. Then we found some parts of the pipe that had structural deficiency, but no signs of SCC or hydrogen embrittlement. And then we had portions of the pipe that had both. So the answer is it's inconclusive to say that SCC was actually part of the pipe break itself. We were hoping to be able to pin that and say, yes, that's definitely the cause. And I think that's where in December, the malcontent in the media and council was, we found the problem, here's the cause, most definitely it was this. And we couldn't provide that because of these inconclusive results, unfortunately, of course. To continue with the results of the pipe investigation, and I'm sorry, maybe what I'll do next time, if I do hear a question, I'll just repeat it for everybody online that can hear. My apologies. The investigation report yielded that the following observations: that some pipes showed visible mortar cracks and delamination upon excavation, while other pipe had intact mortar. So that, to your point, Nigel, some of the pipes did delaminate as soon as we had removed the overburden. The laboratory testing confirmed that some distressed pipes did have chloride attack that had penetrated the mortar, while other pipes showed that there was no evidence of chloride penetration. Soil testing along the feeder main showed significantly aggressive soils in certain areas. And we'll talk a little about that in an adjacent slide, because this is probably, for me, one of the most important points that we've come through right now. Predominantly due to high chloride concentrations. Additionally, severe pitting and corrosion of the pre-stress wires was present, in the pipe that had ruptured. As well too as there were quantities of brittle wire failure. As well, there is evidence of hydrogen embrittlement and stress corrosion cracking in the pre-stressed wires in this particular piece of pipe, appearing to be due to chloride penetration of the mortar and the micro cracking. So that's where we do think that that is the primary cause of this particular piece of pipe failing. Does everybody know, I don't want to assume anything here, do you know what hydrogen embrittlement and stress corrosion cracking is? Okay. Okay, I'll go through it anyways, just in case. So hydrogen embrittlement is the phenomenon where metals become brittle, of course, due to the absorption and diffusion of hydrogen, okay? This can lead to things like cracking and failure of that particular structure. And stress corrosion cracking is the growth of a crack formation in a corrosive environment. Okay, just simply put.
Source of the hydrogen being.
Yeah. That we don't. And sometimes the hydrogen embrittlement would occur actually, and that's what we can't identify, whether it's in situ or it's actually done during manufacture. That's one of the problems that we're still investigating. I know that with some of the hydrogen embrittlement, you'll actually see that when they're heating the wire and drawing it as well, and that we haven't uncovered yet.
Could the chlorides naturally occur?
Stay tuned. This is one of my favorite topics. I got hammered pretty hard on that one in December, so we're gonna talk to that one here pretty quickly. As a matter of fact, we're going to talk about it right now. So, So soil samples obtained by third engineering were gathered at 5 additional repair sites. So if you heard of what was called the 5 hotspots, so immediately following the original pipe break, we had hired a robot, brought in a robot. We had a robot of our own. It was only able to do about 100 meters from the break. We brought in from Ontario a more efficient robot, and we were able to get about 2 kilometers up and downstream from the original break. And that's how we identified the actual 5 hotspots. In fact, actually, the 5 hotspots were well in excess of the requirements that we had for the number of wire breaks that put the pipe at risk. We found quite literally hundreds of locations up and down from the break where we had identified that the pipe was in some form of distress. So quite literally, the pipe was riddled and continues to be in areas having structural deficiency. Ergo, the reason we've put in that monitoring system that I'll talk a little about here. But back to the topic here. So we obtained the soil samples on the 5 additional repair sites, and that information, along with soil samples obtained back in 2014 and in 2024, is illustrated here on the slide. You can see that there are low, moderate, and high levels of chlorides along the entire length of the feeder main. And it's noteworthy that none of these samples showed any sign of aggressive sulfate levels, which is actually something that we would find more typical in Calgary's elevated sulfates in our soils and not elevated chlorides. So what we had in about 2004, 2008 was a feeder main break up at McKnight. And McKnight, the pipe, again, PCCP, it was subject to a sulfate attack. So the pipe actually, the mortar had become talcum. So it was falling apart. It had caused attack on the pre-stressed wires, and then the pipe broke in that form. This was not the case with this, where we're not seeing any sulfate attack. It was actually predominantly chloride attack. So that did take us by surprise. The city's soil testing program tended to focus on sulfates. So this is something that we will be discussing a little later in the presentation, but that's a major adjustment we've made to our asset management program, and our soils testing program is now to start to look at resistivity and chloride as well too, as an indicator of where we might have to do additional testing. Any steel exposed to the soils with high chlorides would be subject to accelerated corrosion, as most of us know, and failure rates. And comparing the wire break data to the chloride data along the feeder main, we are seeing a strong correlation between the level of distress, level of chlorides, and soil resistivity, as I was just talking about. With this said, there are some locations with moderate to severe distress pipes with relatively low chlorides and low sulfates. And there are also areas with high chlorides that don't correlate with severe areas of pipe distress. So that's, again, that where we're seeing that there's outliers definitely that aren't fitting definitely into the mold that we would expect. There are also locations where the 2014 soil sample showed low chlorides, and then the 2024 samples from the same location show significant chloride levels. So I can tell you specifically a story that I had heard from one of our soil testers in and around this break location, or this one of the 5 hotspots here. The testing back in 2014 was in the order of 700 milligrams per liter for chlorides. When we tested it last year, it was 8,000 milligrams per liter, which is, as the soil sampler put it himself, I thought I put my sampling tool in a bucket of salt. It's actually that high of chloride. So it's actually significant chlorides, really quite significant. Something that took us totally off guard.
Did they know the source of the chloride?
Yes. Lastly, it was identified that road de-icing activities using sodium chloride is highly likely to have contributed to the elevated chloride concentrations found in the soil samples. So this was something this is part of the trade-off then when you're running a municipality. On one hand, with levels of service for snow and ice control, the City of Calgary and more Calgarians like to have bare pavement. It's not acceptable, as we used to drive around in our earlier years where we would be driving through 1.5 feet of snow, and that's not the desire nowadays. So as you start to use road de-icers, this is part of the result. You either see damage, as many of you are aware, on our bridge structures, bridge decks, those kind of things. And as well too, you're starting to see now impacts on your underground infrastructures. This was actually something that I do have in my notes here. We made specific note of. We wanted to make, from an engineering perspective, council and the public aware of the trade-off of de-icing materials. While there's a definite benefit to public safety on one side, there's definitely a detriment on the other side. So that was actually quite important for us to stress with council. The city also completed electromagnetic inspections of the feeder main using what they call a pipe robot. And what we call the pipe diver. Now, the diver is not literally, like a 32-year-old guy that we put in a pipe with a mask. It's a robotic piece of electromagnetic equipment that looks like something that NASA would put up into space. It's about 10, 15 feet long, and it uses electric magnetics to be able to sense. It induces the current into the wires, and it can sense that current. And it actually can identify where there's a break in that wire and the continuity of the wire. So that's how it senses wire breaks. So we've used the pipe robot, which is just a tracked vehicle that you would actually put in a dry pipe. And the pipe diver, it actually requires the pipe to be fully in service. So we're actually able to use a hot tap like you would in oil and gas industry. You would hot tap on either end of the pipe that you want to inspect, insert the diver, while it's in flow conditions, and you quite literally insert a net into the pipe at the other end, and you catch the diver. There's nothing too magical about that at all. We actually did lose the diver. I was on vacation in BC, and one of my members said, "Shit, Steve, we lost the diver." It was stuck in a chamber, and they rattled the valves, and the diver popped out, and we caught it again. So the magic of basic engineering, it's amazing sometimes. But so we actually did identify through the use of the pipe robot and the pipe diver a total of 239 locations of the 16-foot deteriorated pipe. So it's, as I said, the pipe is significantly deteriorated in spots. In addition to the pipe that had ruptured, but we put this in context. So of the 239 sections of pipe, 16-foot pipe, there are over 2,000 pipe segments in this particular feeder main. So roughly speaking, it's about 10% of the pipe, quick math, that we are finding in some sort of form of structural deterioration. So the majority of the pipe still is in good condition. And I think that's the problem with giving a message like that to a non-engineer. You can say the pipe is 239, sounds like a lot, and it is a lot. There's a lot of specific areas of risk, but overall the pipe is in good condition. Some people they have a difficulty trying to understand it from a risk perspective. The city completed repairs to the 29 pipe segments from the time of the break in June the 5th, right through the November of 2024. So as you can see in the chart, these actions have resulted in the repair of the segments of pipe that had the most significant structural deficiencies. You can see actually, as provided by Associated, this is the monitor, or this is the criteria that we use to determine which recommended action from a risk-based approach. So we actually had identified that the 5 hotspots were well in excess of a 50+ number of wire breaks. We actually had one location that was 70 wire breaks, and a 60 wire break as well too. So that was such a level of severity and risk that we actually decided to continue with the water restrictions. So because we were going to most definitely have another pipe failure, especially with taking the pipe out of service and trying to put it back into service again, repressurizing, you're definitely at high risk of doing that.
Steve, you keep talking about the wires, but how do they walk? How do they spiral?
Yes, thanks for saying that. Absolutely. So the question here was just tell me a little about the makeup of the pipe, of the PCC pipe, specifically the wires. I keep talking about wires and wire breaks. So how is the pipe constructed? So is it a continuous piece of wire? And the short answer is yes. It is one continuous strand of wire that goes around the entire pipe, call it about, I think it's 481 wraps that you would have in a 16-foot segment of pipe. Roughly speaking, then, if you think of it mechanically, the wire is actually only 9 millimeters spacing. So in effect, one wrap, it behaves as a single wire. So that's where when we call it one wire break, it would be one wrap, that would be one break. The reason being is when that one wire breaks, it actually will release tension, but the amount of tension as it goes through the pipe, it lessens and lessens. The mortar will actually grab hold and not allow it to fully release and not release the wire tension in the entire pipe. So you're allowed actually to have a certain number of wire breaks, and you can see in a scale before it becomes a concern for catastrophic failure. And so this actually is based on City of Calgary data that we had been using for decades and decades now, something that industry has picked up on and other municipalities have contributed to. Hope that makes sense, yeah.
So if it's a spiral of 489 and you try to pre-stress it, you can't pre-stress it evenly along the whole length of the wire.
So that's exactly, so I believe what I'm not, this is where Steve's speculating, I'll say that, not professional opinion, but I would assume as they're wrapping it, that is actually in tension. And so it's just, they keep wrapping it, it's in tension, and just keep pulling it around the pipe.
Steve, I'm not completely familiar with this pre-stressed concrete piping. Is the piping aligned?
No. The coating, if you will, is mortar. It's a cementitious mortar. Yeah.
And is concrete corrosion resistant?
Sulfate resistant. Yes. Yeah.
It doesn't have cover.
And the problem with sulfate resistant concrete, if I go back to 30 years or so ago, it's actually susceptible to chloride attack. And thus the problem. So high chlorides, you think in Calgary that we would have high sulfates, which we do. So you build concrete to what you think is your typical soil conditions, and now you've opened up a problem to now a new problem, which is chloride attack. That's a bit of a learning for us as well.
Wrapping up the wire, is it done as part of the installation, or is it pipe is pre-wrapped from the factory?
Everything's done in controlled conditions in the factory. So the pipe is manufactured at what they call a stick. So a 16-foot length of pipe is a stick. It's all done in the factory and then installed in the field. One of the things that we were thinking about as well too, and that's why it glinted upon the fact, we were wondering that during installation, could it have been mechanically damaged? So maybe a hoe, rested its bucket on top, cracked that mortar. And that's one of the things we're investigating. Did we see obvious cracks as opposed to micro cracking? We didn't see obvious cracks from construction. That was one of the things we were really wondering, was it was just such a very localized attack. And then looking back now with the eyes that we have now, we're actually seeing that it's most likely the chloride attack.
Steve, I see that it's from an ethic inspection, but why is there
Perfect. Now, and I'm sorry, I keep forgetting to repeat the question for the people online. So the question is, so why does this talk about acoustic monitoring if we're using electromagnetic inspection? So the device we use for inspection purposes is the electromagnetic inspection for this PCC pipe. Now that we know we have a baseline, which is here, that we have a number of locations that are still structurally compromised. So using the criteria that's at the bottom, we actually have installed acoustic monitoring across 5.6 kilometers. We just finished it 2 weeks ago installing. So the acoustic monitoring system is fiber optic. And similar to the pipe diver, we install it, we inject the fiber optic and as a parachute, and it gets sucked along the pipe while it's in service. We catch it at the other end, pull it out, and then we do it again. We insert another section and we keep rinse and repeat. And then they will splice together the fiber optic. So we will actually get a full length of fiber optic. That fiber optic senses vibration. So The magic of science, not quite sure, but the magic of science allows us then to sense what the vibration, what the pipe is doing. It can hear, quite literally hear, wire snaps. And it's quite obvious when you hear a wire snap. So now that we know that we have sections of the pipe that are compromised, we listen. So it's 24/7 basis. We're listening actively to the pipe. I literally get an email from our contractor, and that will say you had a pipe break on this stick of pipe. So we can actually, it's to the precision of a meter. So I can tell you which stick of pipe. I can attribute it to every stick has been sensed of what its number of wire breaks are, and I will literally go, oh, that has 5, it has 1 more 6 breaks, or I'm going from 45 to 46 wire breaks, and I can keep listening. But if I go from, say, a 39 to a 40 or a 45 to a 46, I can actually start to pre-plan ahead. I'm coming up to a piece of pipe that could exceed the emergency shutdown point, and so now I can proactively prepare for taking the pipe out of service. So I can notify Calgarians that we're going to be into a water restriction again or something along those lines. And we actually can plan to take the pipe out of service and repair it right away. So that's why we monitor the pipe.
So this is 50 wire breaks within plastic.
That's a great question too. So there's differing opinion. They're saying it's 50 wire breaks within one stick. Is it contiguous or not? So are you seeing it's all 50 breaks in one spot, or is it okay to have a 30 and a little bit of relief and a 20? So there's difference in opinion on the science of that. We're playing it safe from a conservative perspective, and we're saying as long as there's 50 breaks in one pipe. So it can still have a pause, like a section where there's no wire breaks, but it doesn't matter to us. We'd rather actually follow this to the T. I'm not able to tell. I don't think that's, I don't, visually is really, keep in mind, okay, the technology only has, this kind of technology has really only been in place for about the last 15, 20 years. And it's actually been only the last, say, 7 to 10 years where the technology is trustworthy enough. So I don't think coming out of the factory, we could have even inspected it if we wanted to. Sure.
Because you have associated grittiness to 5 spots.
Yes.
And that may well be the problem. It was all external. And the causes were all external.
Mm-hmm.
Then, okay, there's 5 spots.
Mm-hmm.
But in regular pipelining, hydrocarbon pipeline, every single joint of pipe is numbered.
Yeah.
The day it was made, there's no where it was made and what properties it had the day it was made.
Yes.
So if one particular stick that starts to be in the front line, then people look at that and be like, wow, there's more than this. So that's what I'm saying.
Steve, could you repeat that, please?
Steve? I'm loath to speculate. To be honest, I'd love to be able to talk about it, perhaps over a beer or 5. But unfortunately, no, I'm not able to say.
So these pipes are actually sourced from somebody's stockyard somewhere.
Again, I'm not able. I don't know how it was sourced. So unfortunately, we couldn't find records of the actual manufacturer. That actually is documented information as well.
Can I just jump in?
Sure, please.
Hugh's asking if you can repeat the question.
Absolutely. I apologize, Hugh. Hugh, they're just asking questions around the sourcing of the materials and whether there's adequate records about the quality, if I can call it that, the quality control methods that were used. And the short answer is no, we don't have quality control records for any of the pipe that we had purchased back in the 70s.
So I think you just answered my question, which is the picture you showed us of the stick with all the cracks, longitudinal cracks,
Mm-hmm.
they would have been caused by circumferential tension around the pipe, which would have meant that mortar batch shrank. It was greater shrinkage in it than in other mortar batches.
There's a possibility, and that's one of the things the forensic report, and by the way, the forensic report is actually, oh, sorry. The question there was, if the mortar, if I could summate, if the mortar would have shrank during or just immediately post construction of the pipe itself, as opposed to being inside, and that could. So that was one of the things that and by the way, if you go online, you can actually go to calgary.ca and you can actually see the entire report. If you wish to geek out, it's a riveting 680 pages. It's great bedtime reading. Pull it up, you'll fall asleep in a couple of minutes. But no, this is one of the things they had also speculated, and they couldn't tell if it was done pre-construction or post-construction. Unfortunately, that is the fact is, yeah. All they could do is what they see at the time after when they unearth.
But my issue is that there was no quality control on the shrinkage of the mortar.
Maybe, but we don't know. We have absolutely no proof of what construction or the manufacturer technique was at the time.
Which then begs the question, when you're inserting new sections of pipe,
So, sorry?
The new sections of pipes you're putting in are steel.
So we're using, we still use PCCP, depending, we do actually, based on risk and based on the type of pipe. So the short answer is yes. We've changed our quality control methods, our asset management methods. That's something I'll talk about as well too. So our quality control has changed dramatically, including our construction techniques since 1975, 71, yes.
what is the pressure at the system?
Sorry?
What is the pressure?
Oh, sorry. What is the pressure at this particular location? I would have to. My brain is lost the pressure. For this particular pipe, I thought it was 140 for the design.
I think that's what it operates at.
I thought it was 115. Actually, is what I was thinking. Because we exceed 140 is the yield strength on the pipe, if I remember correctly. But I want to be precise in my numbers. I believe, don't quote me exactly, I thought it was about 68 meters of head. So we're looking at, is that about 110, 115 PSI? Something like that. If I'm right. That's, I believe, we set our pressure alarms to 68 PSI. So that would correlate actually to because we actually use for the worst piece of pipe. So if there's, say, for example, a pipe that has a compromised number of wires, 30, we will calculate, and if that's the worst pipe at the lowest point so we will actually use that as setting the operating pressure for the entire length of pipe, for the entire feeder. So that's when we tell the media that we're operating at a lower pressure. It's because of that particular segment of pipe that we're operating.
The design would include transfer pressures, which are much higher.
That's correct. Correct. With the compromised pipe, though, so we actually have to consider that a transient pressure. We have to include that because we do not want a transient pressure compromise that compromised piece of pipe, if that makes sense. So that's where the pressure limit, including transients, any type of high pressure conditions, we set that at 68 meters, if I remember correctly.
And the space that I think you got from, was it San Diego?
Mm-hmm. Yeah.
Was it unique, or what's the difference?
That's a really good question. So for the people online, again, sorry, keep apologizing here. There's lots of questions coming in and over here. So the pipe that came in from San Diego, was it unique or was it the same? So this is part of the challenges with a 1950 millimeter pipe. You don't go to Home Depot. That's the difficulty. It was about 4 of us, myself included. I reached out to friends across North America, from Florida, Toronto, Vancouver. There happened to be a pipeline conference in LA that day, and one of our pipe experts happened to be at the conference. And so I heard from a friend who's in Montreal who went to the conference, met the guy, our Calgary guy, and they were literally walking up to people from various cities. And that's how we found the pipe. It was 2 sticks, they had 4 sticks of 1950. It was absolutely, it's a trash condition. It had been sitting outdoor for years and years and years, and it was their spare pipe. And so they loaned us 2 sticks of spare pipe, and we were able to rig other sections of pipe. So to make the 5 repairs work, we had to weld and spot a bunch of our other materials that we had. So we were rigging pipe as we could. Yeah. Some of the other construction techniques we used a thrust block to hold. There was an existing piece of pipe. It was compromised, but it was well enough. It didn't require a full replacement. So the decision was made with Associated's help to actually just build a thrust block around it. And that's a very common technique that they use in Ontario as well. I'll keep on trucking. These are awesome questions. Thanks. Okay, let's see here.
So if the main culprit seems to be micro cracking and chloride infiltration, coating on water skin now?
No. So not with PCCP. And sorry, I'm not enough of a pipe expert to answer, but I will tell you the answer is no, that we don't use coatings on PCCP. If you'd like to find out why, I'll get your contact information after, and I'll be able to. And sorry, the question to me was, knowing that we know now, and it was micro cracking and chloride attack, are we coating our pipe now? And the answer was no, we do not coat our PCCP pipe, or PCCP, that's redundancy pipe. So as I said, we're actually now continuing with the slide, but with all of the repairs being made, we are now operating with a very few number of wire breaks. In fact, actually, the number of wire breaks that we've had since November is 5. And we actually have only heard 5 wire breaks, and they're on locations that had 0 wire breaks to begin with. So the pipe is just naturally aging. It is just progressing in time. So I'm glad to hear that the pipe, that's where we can confidently say the pipe is actually stabilized. We are still running it, as I said, in reduced pressure, and that's by specific design. With that said, we do recognize that we do have locations of pipe, as I said, that have moderate structural deterioration. So those are the ones that specifically why we spend the money to put in the fiber optic monitoring, so we can ensure that the pipe is still operating safely, and that we give ourselves the fair time that we can accommodate any kind of repairs.
Are you guys doing anything with the soils that are full of chlorides?
The question is, are we doing anything with regards to the soils that we found that are, so that is part of a subject we're studying right now. The quantity of the soils and the location to the Trans-Canada Highway, both either adjacent Trans-Canada or directly under the Trans-Canada, would warrant us to rip up the Trans-Canada Highway. So it's what we're trying to figure out right now. Why did they get there to begin with? We believe it's because of the road de-icing materials, but how to remediate, if you can remediate at all, that's part of the question. You may just, one of the strategies might be recognizing that you have high chloride soils, and now you monitor the pipe and you just do repairs as need be. That also is part of the repair strategy that I'll talk about a little further on, and I'm well over time, but I hope you guys are okay if I want me to keep on trucking. So maybe what I'll do is I'll just pass on through here for the sake of time. So some of the lessons learned that we did get out of this, and please don't get me wrong, actually Calgary does have truly a world-class asset management program with our water utility. Water utilities around the world, you can come to us to see what are we doing. It sounds horrible. It sounds hard for me to say that, because then on the flip side, people ask, well, why did the pipe break? And I hate to sound flippant, but pipes do break. And it's unfortunate that this particular pipe, such a critical pipe in our water network, broke. But then it allows us the opportunity to do a lot of soul searching and a lot of lessons learned. So really, as we've talked about as well too, one thing that we are definitely taking away from this is the learning about the chloride attack and the need for us to actually start to use resistivity testing as a preliminary sample on where we need to focus a lot of our further in-depth testing for chlorides, and then as well to do more either destructive testing or more invasive testing as well too. As well too is starting to look at the other identified mechanisms and factors, focusing on feeder main risk assessment and redundancy. So the back in 2008 and then reaffirmed in 2015, this pipe was considered, of course, highly critical, if not the most critical pipe that we have as part of our feeder main network. But on the flip side, it was considered low or incredibly unlikely to fail. And because of the information that we had at the time was we were doing sulfide testing and we didn't see sulfide attack. And so so the pipe was relatively young. We've been modeling the pipe. We're doing all the things that we thought we needed to do, and the pipe broke. And so what we're seeing now is we're adjusting all of our methods, not just for this particular feeder main, but our entire feeder main network. We have a feeder main network of just over 450 kilometers of pipe, and it's all at various ages and as well to different types of construction. So that's something that we're trying to adjust.
Does that include sanitary feeder mains too?
So sanitary feeder mains, so we, as a lesson learned, yes, we're applying to feeder mains. Ironically, you heard 2 weeks ago that we actually had a sanitary spill into the Bow River. I'm in emergency operations center right now, dealing with that break. We were literally applying the lessons learned to all of our sanitary feeder mains, and this pipe broke. So short answer is yes. We do have a number of siphons. So siphons are river crossings, passes under a river, that are critical. And there's other assets that are critical as part of the network where we have low or no redundancy. So if you remember 15th Street as well too, in the Inglewood area, that's one of the things that we're thinking about as well. So, yeah. As well too is review our design guideline for feeder mains. So things like quality control, things like sulfate resistant concretes, other types of new pipe specs as well. That's all something that we're looking at. On to water system planning. So now coming out of this to provide you a little information about how we plan for the water system. So this is actually, I will admit, outside of my domain of control. It's one of my peers, Sarah Huber. She does, if there's a broken asset, then we'll identify it and assess and we'll fix. Her team is the one that models the entire system, the network, but I'll try my best to parlay the information that she's providing us here. So the City of Calgary's water system is designed to provide a maximum day demand in normal working conditions, and an average day demand is planned for emergency or infrastructure outage. This planning criteria applies to all of our infrastructure, from our raw water intakes to your customer taps. And the criteria aligns to the provincial standards that were updated in 2021. So to give you a little more information, maximum day demand is the highest total volume of water produced in a single day in a given year. In Calgary, our maximum day demand is often on days of 30-degree weather, either in June, July, or August, as you would expect. It'd be weird to see a 30-degree day in January. Sorry, that's a Steve ad in there. Yeah, minus 30, more probable, not plus 30. Average day demand is calculated by taking the total volume of water produced at both of the water treatment plants over the year and divided by 365. In Calgary, an average day of water demand is similar to the demand on a shoulder season day in April or October. Okay.
So how many days would you exceed, your max day? You would never design a hydrocarbon system like that, never. Storage stuff.
Exactly. So we do actually have storage within the pipe itself is storage, and we do have reservoir system as well. There are a number of reasons where we're starting to see, and predominantly growth, we're starting to see that we're bumping up more frequently to our max day demand. So over the past 2 decades, and maybe this helps as well too, so it's not just about building new infrastructure to accommodate for the needs of growth. But over the past 2 decades, Calgarians have reduced their per capita water use by 30%. enabling an overall demand that has been the same since 2003. So even as the population grew by 500,000 people. So if you bought a toilet in the 2000s, I remember myself, and you got your $50 rebate from Home Depot or wherever you were buying it from, that was actually subsidized by the City of Calgary. So it's those kind of non-asset solutions that really go a long way for helping us for water consumption and reducing water consumption. So as I was just mentioning, we've implemented a range of tactics and worked with partnerships with Calgarians since the 1980s to reduce water consumption. While we've made great progress, challenges out of water availability and rapid population growth necessitate continued focus on water efficiency.
Can you just tell me the balloon that orange ones are coming here?
And I'm sorry, I'm colorblind. Truthfully. So on the left side, thank you, exactly. This is orange? Left top is orange, great. And so this is consumption. So in 2023, we're seeing that consumption was 549 megaliters a day. And in 2024, we're down to 454. Your max. In Calgary 2024, 1.46 million people. Sorry, there was just a question for those online. I'm just trying to explain the slide on the left. So the historical overall demand, I should have just read this. The light blue line shows, jeez, Sarah, you got me. The light blue line shows the trend that Calgary's average day demand and max day demand began to increase in 2020. Please note that the demand values for 2023 and 2024 include the impact of water restrictions and cannot be used for trend analysis. The city's updated water efficiency plan and accelerated water loss program are both key initiatives to reduce demand. So we had talked about that. I'll just move on to the next slide. In the near term, as water demand in Calgary increases, the need for major infrastructure, including new and expanded water treatment plants and feeder mains, is required. These investments serve growth in Calgary and the region and provide system redundancy. This infrastructure is complex and challenging to design, and usually resulting in a project timeframe that is well in excess of 10 years from planning to infrastructure being built and put in service. The feeder main project shown on the slide will increase Calgary's water transmission capacity, ensuring there's capacity for the water system to serve growth, to provide redundancy around the Bearspaw South Feeder main, and reduce reliance on our existing feeder mains like Bearspaw. We're also building water treatment plant projects that will increase water treatment and raw water capacity, ensuring that we have sufficient drinking water to supply growth, both in the Glenmore water treatment plants expansion and our new expansion up at the Bearspaw water treatment plant. So, question, go ahead.
So with all this growth and ongoing extension of water lines, etc., how large a challenge is it to maintain consistent water pressure in your home?
Sure. The question was how difficult or how much of a challenge is it to maintain water pressure with all of the growth? I will admit that's not my bailiwick. I apologize. If you wish, I can get you the answer of that. If I were to speculate, I've never heard that we have a challenge trying to maintain water pressure. We do recognize there are parts of the city that are underserviced by pressure and sometimes overserviced as well too, due to either geography, location, adjacency to reservoirs or pump stations, et cetera, et cetera. I'm sorry, I'm not able to answer the specific question itself. Let's talk about the reliability of the South Feeder main. So as we talked about in council in 2024, we're continuing to operate safely the Bearspaw South Feeder main. And while the North and South Calgary water servicing projects, so those are the two that you saw literally splitting from Bearspaw to the north and to the south, they'll allow us to move water adjacent to the Bearspaw South Feeder main to supply water during the average day demand. The feeder main, we still require it to provide maximum day demand. So we will continue to rely on the Bearspaw South Feeder main. So that is one of the reasons why we're spending so much time and effort monitoring the pipe. We can't just decommission the pipe, take it out of service. We will continue to require that pipe. In order to improve the reliability of the 1950 pre-stressed concrete cylindrical pipe, we have several rehab and replacement options that's currently being identified now. Those options include open cut pipe replacement, external reinforcement, internal lining, and microtunneling of the new line. Now you can see that the location, I guess that's in the next slide. Actually, I'll just continuing here. I'll show you in the next slide what the proposed alignment looks like, but the microtunneling option is the option that we select as the most promising at this time, as the construction technique minimizes traffic impact and water service disruption, as well as minimizing impact to adjacent homeowners and businesses. So if you're familiar with the location of the feeder main from the previous photos, but you can see it roughly here, the Bearspaw feeder main runs through on the south side of Bowness. There's actually a personal friend of mine that lives on 33rd Avenue, right in the middle of where the feeder main exists on her street. So of course, we're very mindful of community impacts, both immediate community impacts and plus as well to the adjacent community impacts because of the proximity to businesses along 16th Avenue and within the Bowness community. We did get a lot of traffic shortcutting as you would expect as we're doing construction to try and fix the feeder main. So that's the reason why we would propose a microtunnel option. So it's a very deep tunneling, a tunnel boring machine that we put in with shafts, and you put the pipe quite deep in the ground to avoid altogether. So it's going to be a two-phase approach. The first phase is the section here from Shaganappi Trail, Edworthy Park, roughly speaking, all the way up to the Bow River crossing, what we call the Rona. There's a couple of locations, hotspots in around the Rona location. And then the second phase of work would be on the other side, the west side of the river, heading right up through to the Bearspaw treatment plant. One of the options we're looking at as well too is either leveraging a new right-of-way along CPKC, the rail line. That would allow us to do open cut as opposed to a more expensive microtunnel option. But that's one of the other things we were thinking about as well too, but now you're looking at a whole host of other issues with Department of Fisheries and Oceans, regulatory, you know the world if you're from oil and gas. We're looking at all of these options and trying to balance off the cost effectiveness as well too to community impact. Mindful as well too that any solution we choose, we have to tie into the original pipe and at the plant. So there will be inconvenience to the public as we take this out of service. So what we want to do is also time it so that it's in low water use season. So we're not worried about max day demand, we're worried about average day demand so that we can, this is why it would be a multi-year approach so that we're minimizing impact to Calgarians, hopefully never having to turn off the water taps.
So
microtunneling
will go under people's houses?
Literally under.
Live in their houses?
Absolutely.
When you say deep, how deep?
I don't know. That's subject to the detailed design. We'd have to figure out where stable material is, bedrock, etc. That's part of the detailed design as well too, is with the microtunnel, do you put in another 1950? Do we size for growth? Are you doing multiple pipes as opposed to one pipe? So now you have redundancy, but even with a smaller pipe, et cetera, et cetera. There's a lot of options. So it would be sorry, I keep forgetting for online friends. So questions were how deep? I don't know how deep. the kind of material, how big would it be? Would it be a 1950 or not? I would expect that the tunnel itself would probably be larger than 1950, and it would be basically, it's a conduit, it's pipe in a pipe. So I don't know exactly what the design, if it would be multiple pipe or just one pipe that you would put inside. That's something considering. And the question there was, what materials would you use? That I don't know as well too. If it would be steel pipe, it would be either PCCP or steel pipe. But again, we actually do that based on now risk profile. So learning from what we've learned here, what kind of pipe would you use would totally depend on the risk of building and inability to access that depth of pipe. It's widely used. Since the 1970s, it's been used. It's actually the challenges that we have. It was PCCP that blew up in weeks after in Montreal. That was pre-stressed concrete cylindrical pipe. In Halton, Peel region, Niagara, it's quite common to have PCCP as well too. It is a standard pipe and it continues to be a standard. It's specifically this vintage, this class of pipe that they do have notable issues with. So it's this era of construction of pipe from the mid 70s to about the early 80s that they did have issues. PCCP still gets continued to be used today, and it actually is very safe pipe. It is reliable pipe because of the changes in quality control and the types of materials that they're using and methods of construction, especially the steel itself. That's the issues that they were having with hydrogen embrittlement and stress corrosion cracking and micro cracking as well.
Sure, someone will have done an energy study in terms of how much energy would be required to make steel pipe versus concrete pipe. One of the virtues I think of micro tunneling is that you can share the cost with other utilities because
so there's a trade-off, and so the comment that was just being made for those online is the energy study of whether or not using steel pipe versus concrete pipe, and that exactly would be part of the analysis, and as well too as risk to the various type of pipe materials, I should add, but as well to cost sharing agreements with that particular pipe. I'm not sure if the city with an asset of this type of criticality would want to put a gas line inside there. Just from we already have issues with specifically a high pressure transmission lines adjacent to some of our manholes. If we do need to do emergency work, like right now we're doing with that sanitary pipe, there is an immediately adjacent line, and we're having difficulty doing any work in and around the manhole to access the pipe because of the siting of that high pressure transmission line. Sorry?
Have you ever considered lining the pipeline?
The interior of the pipe?
Yeah.
So we did consider one of the options for the rehab of the pipe was lining. The fact that you can only line, so slip lining, you need to do in straight shots. And there are a number of bends. This is overly simplified, just a straight line. There are numerous bends. So every time there's a bend, you're digging down to the pipe, you're exposing the pipe. And it's quite a large hole, quite a large shaft, because you're literally jacking a pipe inside that pipe. And so it becomes very invasive to especially road traffic, because this is quite literally under 16th Avenue in the old Motel Village area. So we did consider it. It's still one of the things we're considering for where we have just a very high concentration and it's quick and easy to get in to slip line some of the work. We are considering. We also look at wrap on the outside of the pipe. And the concern we have is by unearthing that pipe, now if it's structurally compromised, are you actually putting at risk now from a public safety perspective, because you're removing that overburden might be holding the pipe together. And that actually is an interesting one. So we did expose a section of pipe, Crowchild Trail and Memorial Drive. If you remember, the off-ramp was shut down for a few months there in around Kensington area. We had excavated, we identified there was high chlorides in the area, and our construction engineer could quite literally hear the wire snapping as the overburden was removed. And we had identified there was about 30 wire snaps in the location. And when we hydroblasted the pipe, it had become 80. So that is actually a concern we have, is touching the pipe, removing overburden in a spot that might be structurally compromised.
Does PCBD might have a protection, or how does?
No, PCCP does not. Well, our steel pipe does. We do have a cathodic protection program. Since I'm trying to think, the Roy Brander days back in 1998, 2000, this old friend of ours here that worked at the city with us and leaned in hard on cathodic protection. And actually, got to say, the water utility, thanks to that, we saw our breaks, number of annual breaks, go from 1,800 breaks, I think it was, per year, to about 200 to 250 that you're seeing now. So we have a pretty aggressive cathodic protection program we're still benefiting from. But you can't put cathodic protection on concrete pipe.
What about on the wires, stress wires?
You can't put they were just asking for those online, can you put cathodic protection on concrete pipe on the wires itself? And no, you can't. Yeah, you're compromising the integrity of the pipe.
I see.
Have you thought, this may be a silly question, have you thought of dosing those areas of ground with high chloride concentration, dosing with alkaline solution?
No. So not to sound obtuse, and yes, but that's still something that we're trying to figure out as well too, is so we don't have a program like that for the city. So the short answer, sounding horrible, is no.
Because you are spending significant resources measuring the chloride concentration. So
Yes.
you know where you need to neutralize the soil.
So we don't know. We found that there's very localized areas of high chlorides, even on this pipe. As I said in the report, there are spots where specifically around 16th Avenue, that motel village, that's where the high chloride concentrations occur. We don't know if that's irregular for the rest of our feeder main network. And that's where we're doing the soil sampling as a first step towards understanding, or do we have other pipes that are at risk, or do we need a larger remediation program like that?
Because it would be an additional arrow you put
It's true.
if you have a hotspot.
It is true. And so this is actually part of our first step, is to identify, do we need those additional arrows? This is where we're looking at this, trying to do those tests on those other parts of the other parts of it. I apologize for taking you way over time, but it's been an absolute pleasure talking with you all. Thank you.
I'd say we should thank Steve. One of the most informative talks we've had, and we apologize for all the questions.
Don't, no. I'm gonna stick around. I'm gonna have a beverage here, so.
Definitely the techno nerds who wanted to meet on council but didn't get to.
Yeah. Oh, thanks.
Because you gave that talk tonight, CPGC has donated to Operation Eyesight, and the person named in here has received sight because of our talk. So thank you so much.
Guys, make me weepy. Awesome. That is actually truly meaningful. I really appreciate that. Thank you for doing that. Thanks for having me. I'd love to stick around as well too if you'd like to geek out for a little bit. So I think my kids are probably already going to bed. So whatever. What's another? Go ahead.